I'm Karthik Sriram, a PhD student from Yale University, advised by Abhishek Bhattacharjee. Today, I'm going to present our work on the design of flexible, general-purpose, implantable brain-computer interfaces. This work is a first step in a longer-term research project in realizing a fully functional brain-computer interface in collaboration with people from Brown and Rutgers universities. This field is incredibly exciting and offers promise in treating neurological disorders and understanding brain function. However, it requires principal hardware-software co-design to overcome some of the challenges that it currently faces. In this talk, I plan to show how we can take lessons from architecture and software engineering and apply them in this field. I'm saying several things here which may naturally raise some questions, such as what are brain-computer interfaces or BCIs, and why are they important? Why should BCIs be flexible? Why is that challenging? I'm going to walk through each question in this presentation and answer it to hopefully paint a better picture of the current state of BCIs. I'll then talk about how our community has the tools to enable such a flexible BCI design using the principles of hardware-software co-design. As a demonstrator for how to develop a BCI platform, we evaluate our design from wet lab experiment data all the way up to chip tape-out. We use electrophysiological data collected from the motor cortex region from non-human primates to test and evaluate our design. We've taped out the first generation of our design, Halo, using industrial libraries. Going forward, we envision multiple generations of tape-outs, each progressively implementing more and more functionality. The key takeaway from this work is that it is possible to use principal techniques from software engineering and co-design that with hardware to realize a flexible architecture and bring the best of both specialization and general purpose. Broadly speaking, this work can be applied to ultra-low power multi-accelerator SoC designs. With that, I'm going to begin with what are brain-computer interfaces and why are they important. Brain-computer interfaces, or BCIs, are a nascent technology that are used to capture and influence the activity of biological neurons in the brain tissue. These BCIs are currently being used to improve our understanding of brain function. BCIs have also demonstrated use in interfacing with the digital world. Researchers have demonstrated the use of BCIs for paraplegics to control prosthesis, for example. BCIs are also being used to treat neurological diseases such as epileptic seizures by electrically stimulating specific locations in the brain. In fact, the FDA has already approved the use of BCIs to treat the following disorders, with more to come as research in this space increases. BCIs are currently in use by over 160,000 patients worldwide, and this number is growing by 12,000 each year. Companies are also interested in designing BCIs. Neuralink, for example, is developing technology that targets reading from thousands of neurons at high fidelity. Higher fidelity of data enables the treatments I just mentioned and furthers research on brain function. Currently, the highest fidelity is achieved by invasive BCIs, which are surgically embedded directly on the brain tissue, allowing them to record and stimulate a large number of neurons at a high resolution. Non-invasive BCIs also exist and are realized as wearables that are placed directly on the scalp to deduce brain activity. The signals they collect are noisy and low resolution than invasive ones, making invasive BCIs the better choice to further research in understanding of brain function. Our work in building Halo is focused on the invasive class of BCIs. However, where we depart from traditional designs is that we focus on building a flexible device. Let me explain why this is difficult. A typical BCI is powered by single-use non-rechargeable batteries, rechargeable batteries, or by inductive power transfer. For BCIs to be safe for chronic use, they must not excessively heat surrounding brain tissue. This in turn means that they are power constrained. How power constrained? The paper has a lot of details on the range of acceptable numbers, but we're going to go with 15 milliwatts for the remainder of this talk because this is generally considered safe enough for BCI implantation in multiple brain regions and at multiple depths. In this power budget, BCIs need to do everything, starting with recording using sensors. These sensors are electrodes used to record primarily neuronal electrical activity, ranging from single electrodes for individual neurons to arrays of hundreds of microelectrodes with a Utah array, as seen in this image. These arrays are very small, in the range of millimeters in size, and cover thousands of neurons. Current state-of-the-art sensors produce data rates at 46 megabits per second, which is almost as much as 4 high frame rate Full HD videos. It is important for BCIs to record from as many neurons as possible to enable further research and treatment in this field, with initiatives from DARPA aiming to record from millions of neurons in the future. These high data rates from the electrodes are then processed by some kind of logic, say a microcontroller or some ASIC. The tight power budget constrains the logic heavily, but the logic on the BCI can do several complex things. As an example, the data can be processed to determine whether a seizure is taking place. After processing, the logic can also decide to electrically stimulate neurons to treat neurological diseases. This is an example of a closed-loop system where the logic processes the data, for example, to detect seizures, and when a seizure is detected, electrically stimulate specific brain regions for treatment. There's also often a real-time need of a few milliseconds to process the data, which amplifies the need for performance even more. For example, to allow control of prosthesis for paraplegics to mimic a human arm, BCIs need response time in a few milliseconds. Alternatively, the data can be passed off from the radio for offline analysis. The BCI is then hermetically sealed in an area less than 1 square centimeter for the entire package. To summarize, safety is critical for BCIs, which leads to a power budget for the entire device. We assume a limit of 15 milliwatts for our design, which is known to be safe and is discussed in the paper. BCIs require processing very high data rates, with the state-of-the-art producing 46 megabits per second of data. This number is expected to rise, with many targeting millions of neurons for analysis in the future. There's also a need for real-time processing on the device in the order of 5 to 10 milliseconds. All of this points to requiring a highly power-efficient design. In this graph, I use data processing bandwidth as a proxy for capability of the device. Due to these constraints, BCIs targeting high data processing bandwidth have thus far been realized with custom ASICs that treat only certain diseases or perform specific tasks in specific brain regions and thus trade off on flexibility. However, there's a case to make BCIs more general purpose that is needed for wider BCI adoption. Neuroscientists have found that treatment often needs to be specific to individuals and brain regions. Treatment efficacy improves when it is tailored to an individual, thus making flexibility desirable. Current designs also architect a BCI device for one treatment and/or for specific brain regions. To reduce the cost of scaling up, we instead prefer a more homogeneous platform that is flexible enough to target multiple treatments, brain regions, and can be tailored to an individual. Finally, the FDA approval process for a medical device takes a long time. On average, this can take 3 to 7 years. An alternative approach in the FDA approval benefits from a modular design. In addition, it will be very beneficial if the device targets multiple treatments once approved. We are not the first to notice this. There have been designs proposed which are flexible and target multiple treatments, but trade off on processing less data to do so. Ideally, we would like to have both, being able to target a lot of neurons, but also flexible enough to target multiple treatments with the same device. In summary, we established the following design goals for a BCI. That is, a design that is safe, is capable of processing high data rates, and has a flexible and modular design. Now, I'll discuss how we can use known architectural principles for accelerator and hardware-software co-design to meet these goals. At a high level, our goal is to be flexible by supporting multiple classes of workloads. These selected workloads are common in BCIs and cover different treatments, from dystonia to epileptic seizures. There are also examples of workloads used to further research in this space and to understand and analyze brain function. We discuss each of these workloads in detail in the full paper. In order to support these workloads, we first try the completely general purpose end of the spectrum by implementing these workloads in software for a low-power RISC-V microcontroller. However, as I'll show later, this far exceeds the power budget that we established earlier in the presentation. Now, we go to the other extreme and build custom ASICs for each task, which we call the monolithic ASIC design. Here, I show multiple tasks for each category of our workloads, color-coded as seen on the right. In this case, the microcontroller is only utilized to manage these ASICs. This kind of design scales poorly with area, since some functionality is implemented multiple times in different tasks. We find that this too is not under power budget for some of the workloads. Thus, to meet design goals, we need to design something more fine-grained and use hardware-software co-design where we decompose each ASIC further to exploit more optimizations. In designing Halo, we first inspect the software for the workloads we want to implement. We find that algorithms often operate in high-level phases. A phase manipulates similar data structure and performs similarly complex computation, as I'll discuss shortly. Furthermore, we find that the inefficiency in the monolithic design comes from running these different phases at the same clock frequency in hardware. Since some phases are relatively simpler, there's an opportunity to lower the frequency of these components to lower power, a standard architectural technique. Thus, we break down algorithmic phases into hardware tiles that we call processing elements or PEs. Then Halo exploits two key ideas to reach a flexible design. One, we run each PE at the minimum frequency required to sustain performance. And two, we share and reuse common PEs to make judicious use of hardware and save area. These 2 points are at the heart of the co-design principles we use to design Halo. This is the architecture we ultimately end up with when we apply those techniques. This is a massive diagram, so let me take a step back and explain each task by breaking them down into individual processing elements. After that, I'll talk about the co-design principles that form the basis for these decisions. Again, each task is color-coded as can be seen in the legend on the bottom right. We begin with decomposing LZ4, a popular lempelsive-based compression known for its fast implementation. Using the techniques I discussed shortly, LZ4 decomposes into its 2 constituent phases, an LZ phase which finds lempelsive style matches and an LIC phase which encodes these matches using linear integer coding. By decomposing LZ4 into 2 pieces, we are able to separate out the complex LZ phase from the relatively simple LIC phase, allowing us to clock each of them at the minimum level needed to sustain performance. This makes each processing element highly efficient. Next, we have LZMA, another lempelsive-based compression, which is used for achieving very high compression ratios. Since LZ4 and LZMA are from the same family of compression, their first stage can be shared naturally. This allows us to reuse the LZ module as shown by the highlight in orange. This shows judicious use of resources and demonstrates that Halo is indeed a modular and extensible design. Next, we have DWT-MA, a compression workload where we use the MA and RC part of the LZMA algorithm to encode discrete wavelet transformed input. Again, this shows the reuse of MA and RC processing elements. In this manner, Halo's design scales nicely with area, unlike the monolithic ASIC design. Next, we cover spike detection using DWT. This breaks down into DWT and THR PEs, where THR is a simple PE to perform thresholding. This is an instance where we find the reuse of a processing element across different categories of workloads, compression and spike detection in this case, again demonstrating the modularity in our design. Spike detection using NEO or nonlinear energy operator is another example of reusing PEs where computation is similar. It is broken down into the NEO and THR PEs. Similarly, movement intent can be decomposed into an FFT and THR PE. Seizure prediction uses FFTs, bandpass filters, cross correlations, and support vector machines internally. Again, we see the reuse of FFT in this case. Finally, we have AES, the encryption PE. The output of all the other workloads, the compression, can get piped to this PE for encryption. Now, let me walk you through the principles used to make decisions for the design. These principles impact hardware through software and vice versa. In the interest of time, I'll walk through these three principles. The other design principles that we use is discussed in detail in the paper. We shall first take a look at PE decomposition. PE decomposition breaks down the algorithm into individual PEs that feed input to the next in a pipeline fashion. On one extreme, PE decomposition can decompose at the algorithm granularity, giving the same design as the monolithic design. On the other hand, PE decomposition can be used to realize each arithmetic operation as a PE. This gives a wide configuration space to break down each task. As an example, consider the seizure prediction task. You can implement this task, which internally uses FFTs, a bandpass filter, cross-correlation, and SVM in order to predict seizures as a monolithic ASIC. This results in the ASIC running at a high frequency and using high power, exceeding the power budget. The computation in this task is clearly uneven. For example, filters do not need as much computational power as cross-correlation. We find that the commonly used computations, such as signal processing algorithms, are a good indicator of PE boundaries established in software. In this example, FFTs, BBF, cross-core, and SVMs are self-contained computations and thus can be naturally decomposed as seen on the right. This also inherently exploits parallelism and pipelining in the task at a coarse level. By inspecting the code, we can find these decomposing PEs naturally. This optimization gives almost 3x improvement in power in this case, going from 18.7 milliwatts to 6.2 milliwatts. With locality refactoring, we try to refactor algorithm in cases where such natural decomposition is either not clear or not very useful. Let's take the example of LZMA, the compression algorithm we saw earlier. LZMA has two distinct phases. First, finding an exact match in the data to compress, as highlighted in blue, and second, manipulating counter data structures to find probability and encode it as optimally as possible using range coding techniques, as highlighted in green. A natural decomposition will allow us to decompose this into an LZ phase, which finds the match, and an MA phase that finds the probability and encodes it, as seen on the right. However, we find that such a design is unable to meet safety goals. To solve this problem, we refactored the original algorithm to make it more amenable to PE decomposition. To separate algorithmic phases, we realized that data locality, that routines that manipulate major data structure, is a good indicator of kernel boundaries within programs. As an example, consider the code in green and red. These routines manipulate the counter data structure and don't require sharing large amounts of data. Thus, we can separate out these phases, as seen on the right, in order to exploit more PE decomposition. In this case, PE refactoring improved power by 2x of the MAPE. As already demonstrated before, Halo finds significant reuse in processing elements. By decomposing the algorithm into their core kernels, we are naturally able to find kernels that perform the same computation, albeit with a slight variation. Take, for example, seizure prediction and movement intent. We find that both these algorithms use FFTs. While seizure prediction requires a 1024-point FFT, movement intent only requires 25 points. Thus, the FFT PE can be easily shared by making it slightly configurable. This speaks to a more modular design that allows us to be flexible and saves power, roughly 1.7x area overall. To summarize, we refactored the original algorithm into distinct kernels, pruned them, and shared common ones. Each PE is operated independently in its minimum clock frequency required to sustain performance. We use an asynchronous circuit switch network to achieve this. We also use a low-power embedded microcontroller to configure PEs into processing pipelines and support computation for which there are no PEs. This allows Halo to utilize specialization to remain power efficient but also be flexible to support many workloads. As I mentioned at the start, to evaluate our design, we go from wet lab experiment data to functional simulation to chip tape out of Halo. For wet lab experiment data, we use electrophysiological data collected from the arm and leg region of the motor cortex of a non-human primate. This primate performs different tasks, such as walking on a treadmill, reaching for a treat, avoiding obstacles, and so on in a plastic enclosure. We evaluate our design on data collected from these experiments. We design and test all of Halo's components using a commercial 28nm CMOS process. We have performed functional and timing validation with a margin for all Halo components. We have taped out a modified RISC-V core with all the hooks necessary to interface with the rest of the architecture, with plans to include other components from Halo in future generations. We established the following evaluation goals for this work. In the interest of time, we'll cover the following goals, while the rest can be found in detail in the full paper. We compare Halo to different design points in the generality versus specificity design spectrum. Consider the following graph. Here, we plot the total power utilized by each workload on the y-axis, meaning lower is better, in a log-based scale. The red line indicates the 15 milliwatt power budget established earlier in the presentation. Now, our first comparison is with the RISC-V microcontroller, which stands for a complete general-purpose design point. We run each algorithm in both single-core and multi-core designs and report the best configuration for each task labeled on top of the graph. Secondly, we consider the monolithic ASIC design, where each task is implemented as an independent ASIC, shown in green. Finally, we have our Halo design point, shown in gray. The takeaway here is that Halo uses less power than both monolithic ASIC and the RISC-V approaches, with many magnitude improvements for some tasks. We also perform per PE power analysis in the full paper. Please read that for more details or contact offline to discuss further. In the future, we plan to work on multiple generations of Halo to progressively implement more features. In this work, we do an initial exploration of workloads, but this list is not exhaustive and can be expanded upon. We also think that there's an open question about how a network of these implants will work in the brain. Thank you for watching this talk, and I hope to answer questions in the Q&A session.